Hey guys, it's Coach Zaid here, and in this video I'm going to be explaining how to make your robot drive perfectly straight on a black line using Python. So if you have a Spike Prime robot, this video is going to be really helpful to making sure your robot accurately follows a line, whether it be a curved line or a straight line. So I'm going to be explaining to you how to make that perfect line follower to follow that line really well, and to, if you're on an FLO map, hit your missions accurately and get as many points as possible. So this video is going to be sectioned off into a few different segments. So after this introduction, I'm going to do a quick explanation onto the logic of the line follower and really explain the crux of how it works. This is extremely important, especially if you're using Python, because it's not only important to understand the program and the lines of the code, but to understand the logic and the understanding behind it. And if you understand that, that's actually going to be really helpful, because then you can edit this program to make it really well for your situation. Or if you lose the program, you can create it from scratch just by knowing it in your head. So I highly recommend watching the explanation before moving on to the code, which is going to be the third section. However, I'll put timestamps below if you want to skip around. So without further ado, let's go over to the iPad and let me explain what the line follower actually is. Okay, so we're over here on the iPad, and now what we're going to do is explain how the line follower actually works. So before we actually go into the deep crux of the line follower, let's see what the line follower is actually following. So some people have a pretty simple misconception. They think the line follower is following this black part of the line or this white part of the line. Actually, that's not true. It's following in between the black and the white. So that's the really first important thing you need to know. What is the line follower actually following? In between the black and white. So why is this important? Well, the reason it's important is because the first thing we need to do is actually calculate the light intensity we want to follow. So as you can see, we have a small demonstration of a color sensor over here. So how this works is the color sensor actually emits one light here. So it's like a light blue light. I'll change my color to green. A light blue light over here, and it emits that light downwards. That light will then get either absorbed or reflected depending on the color. So you may know from science that white will reflect a lot of that light, which, as you can see in this blue, that'll be a higher percentage. And a black will absorb most of that light. So with the light blue, if it's over a black light, a lot of this will basically get absorbed. And of the percentage, so if 100% of the light is is gone down, maybe a low percentage over black, like 50%, will go up. Whereas if it's over white, a higher percentage, because it really reflects, not absorbs, that will go back up to the color sensor. So this is the first really important thing you need to know. And before we actually do the line following, you first have to get your value, your number of what you're going to follow. So what I've got here is a simple explanation of how to get your value. So the first thing you're going to have to do, as you can see over here, is go to the top left section and you'll see the ports. From there, you'll click reflected light on whichever port you have your color sensor plugged into. From there, you can now push over slowly that light. So as you can see over here, the color sensor on the right is being now over black, so it's about 26%. As I move it over to the left, you can see that number goes up to 50, and now it's in between, which is about 73 or 80. This is exactly what you need to do with your robot. You need to see what number is perfectly in between the black and the white. So with that being done, we can now move back to understanding of what's going on, right? So as you can see here, I have my target value of about 70%. For you, this may be somewhere different, but it will be pretty high, right? It's not going to be somewhere low, 20 or 30, because Spike Prime robots see black at about 50% and white at about 90 to 100, which means the in-between, between 50 and 90 is about 70%. So let's now go on to the explanation, right? We know that this value over here in the green, that's going to be about 70% reflected light intensity. So when the robot's traveling, what it will do, it will first go on this black line, right? It's going to follow it perfectly. But then slowly, what happens is it actually veers off track, right? It may go onto the black. What happens when it's onto the black? To the 70, does it read 70? Actually, it doesn't, right? Because the current intensity, as you can see here, it's going to go downwards because black absorbs a lot of light. So if it's onto the black, what we're going to get is a reflection value of maybe, let's say 30. So I've put it at 30 just for the sake of explanation, as you can see here. So what we do is we use a rule. This rule is 70, which is the in-between, minus whatever it's reading currently. So in terms of the example that we have here, that's going to be 70 minus 30. What is 70 minus 30? 70 minus 30 is simply 40. So what this is, right? Basically, this is going to be the steering power to go back. So what this red line is going to do, it notices, wait, hold on, I'm too far onto the left. My steering power, I'm going to apply a 40% steering power to then travel back there. Now let's do the opposite, right? Let's say it keeps going, but then it veers off to the white now. What does it read on the white? So on the white, we know that it's a higher number. Let's just say it's about 90. So what's our rule going to be? Our rule is going to be 70 minus 90. So 70 minus 90, this is going to be negative 20. As you can see, we're now going to steer back the other way, right? It's a negative number, which means the steering is now going to be toward the left. And this is how the line follower works, right? If it veers off to the black line, it will notice it's gone down, so it's going to go to the right. If it veers off to the white line, it'll know that the light value is going up and it'll steer back to the left. And this whole, this zigzag motion you see over here, it's quite common to see in line followers and other things. This is what we call proportional logic. If you've already watched the gyro straight video, then you'll know that this is quite common. Proportional logic simply means whatever mistake you make or whatever mistake the robot makes, go back in the other direction, right? So if it's veered too much to the black, move back into the middle. To the white, move back into the middle. And it does this with this simple rule, as you can see over here, 70 minus the current intensity. And this rule is actually going to be applied in the program, which we'll come to see later. So that's the basic essence. The one thing that we haven't discussed is something called the LFPK. So what we do, right, I'm going to delete most of this stuff, as you can see over here. I'll delete the red. Okay, perfect. So what we're going to do is I'm going to explain the LFPK. Essentially, what the LFPK is, it's a number, right? I'll explain it further in the program, but essentially what we're going to do is we're going to multiply this correction that we just explained, right? This correction over here and these examples multiplied by a number called LFPK. This is called the line following proportional constant. It basically improves the rate of correction or decreases the rate of correction. So I'm going to use two examples. I've got example 1 in green, and I'm going to do, let's choose purple for example 2. For example 1, let's do correction. So whatever the correction is, it doesn't really matter, times 0.5. And actually, let's make that 0.5 in green just to match it. And for the other one, I'll just copy paste it over for the sake of time. And let's do it for the second one. Let's do a correction of an LFPK of 1.5. So this is how I'm going to explain what the LFPK actually does. In the first situation, as you can see, it's about 0.5. The rate of correction is going to be low, which means your line follow is going to look like this. It's going to be very curvy and it's going to, slowly get back into direction. Whereas if you have a higher number, so that was situation 1. Let's do the purple situation, which is a high LFPK. It's going to be, very zigzaggy, as you can see over here. So it's going to do more corrections because the corrections are happening faster. Now, the actual answer is somewhere in between. So you don't want something too high and don't want something too low. And I'll go into, how to find the perfect LFPK in the programming. We'll do some actual tests later in the video. But that's pretty much it. If you understand proportional logic and where this LFPK number what it generally does, then you're pretty much ready to start programming. So let's go back onto the laptop and see how we can code this. So we're back here on the laptop and now we're going to actually start coding the line follower. So I'll go to the Spike Prime app and new project, Python as always. And here we go. So as you can see, I have the opening part of the app open. We're going to close this knowledge base as always. Once again, it's pretty helpful, but with this video, you can just refer to this. And we're going to delete that part. And now we're going to do our initialization as always. So if you haven't really been familiar with this Python environment, I highly recommend watching the introduction video, which I'll link somewhere up here. This is where I explain the whole environment from top to bottom. So watch that before coming to this. However, if you already watched that, then we're good to go. As you know, with our code, there's always two sections. We always have the initialization part and then the execute code. So let's initialize our components. Initialize components. Let's add a comment just to make sure that it's understandable to us. So we have our hub as our Spike Prime hub. We have our motor. So we're going to initialize one motor for this code. And to do that, we're going to go motor bracket A. Let's make that like this. Make sure you have the capital on the M on, after the equal sign. And then we have our motors, which is going to be plural. and then this is where we're going to put our motor pair. So it's important to initialize both the motor and the motor pair because we're going to be using both of them in individual situations for our line follower. So make sure you've got these two lines properly there. And of course, because we have a color sensor on our robot, I didn't mention this in the introduction, but make sure your color sensor is in the correct position. So it shouldn't be too low to the ground, so it's hitting the ground, but not too high so it can't reach it. Normally 1 to 2 holes, of these Lego holes, 1 to 2 holes away from the ground is a pretty good number. Even 3 holes up works good, but as soon as you start going above like 4 holes, and if there's like no holes, so too high or too low, it won't work. So once we have our color sensor in, we have to initialize it. So we're going to put color equals color. So I've put color over here because this is what I can call it. It's the variable that I choose, and I've got the Australian, or I guess the English spelling, and then here we have the American spelling because this app was probably developed by Lego, which is, I guess, American company or Danish. I don't know. It doesn't really matter. Perhaps the programmers decided to use color. It doesn't really matter. Make sure this is exactly as you see it over here. So color sensor, and I've got mine in C. And then over here, you can call it whatever you want, whatever spelling you like. If you don't really use a U, you can just put it like that. However, I use the U. So I'm going to leave it like this. So this is exactly what we need to initialize just for our line follower. If you have more things like a gyro or a different line follower, a different color sensor, you can initialize anything you want. But just for this video, that's all we need to initialize. Let's move on to the execute code part. So we're going to put a section here called execute code, and let's drop a line. So first thing we need to do, as always, is reset the degrees counted on our motors. So we're going to go motor dot set underscore degrees underscore counted, and we're going to set that to 0. What this line does is it essentially makes sure that whenever we're starting the robot, these motors know that they're at 0, and so they'll hit a certain value of like 360 always, right? If you don't do this, if it's traveled 360 in a previous line, then it'll think that I've already done 360, why do I need to go again? So resetting to 0 is always important because when we measure the distance out, it needs to be from a set point like 0. Now that we've done that, we can move into the crux of the code. So the line follower is going to be sitting in a loop, a while loop to be specific. And what a loop is, it'll repeat a certain action over and over and over again until a certain condition has been met. So with this while loop, I'll write it out first. So while, and then the condition that we're going to use to make the robot stop is the distance that it's traveled. So much like the line follower, if you watch that video, we're going to use motor.get. If you haven't watched that video, it's fine because I'm explaining everything from scratch anyways. Counted, and then don't forget that greater than negative 800. Okay, so depending on if your motors are flipped, positive or negative, you may have a negative number here, a positive number here, but I'll explain that a little bit later on. In this while loop, make sure you have a colon over here. So if you don't have a colon, when you press enter, it's going to go to a number 15 normal line. If that's how you know you've forgotten your colon, because if you have a while loop, you put the colon, it'll actually tab it up. So if you can see here, if I write lines, there's like a little special line over here, and that's going to be because everything in the while loop has to be indented slightly. So that's our indent over there, so we know everything's good. So this is our condition. Let's get into the actual correction part. So for the correction part, I'm going to write out a few different lines and then explain everything. So we're going to need something called the LFPK, and I'm going to let the LFPK equal 1. We're going to need something called steering, and I'm going to let the steering equal I'll get to the steering later, as always, just because it's a more complicated line. And then we're going to go motors dot start. We're going to put steering up here. Make sure this steering is exactly the same as that steering. So when I highlight that one gets highlighted. And then we have 15 over here. And I won't put a space in just because it gets too crazy. Spaces or no space, doesn't really matter. That's your personal preference. And we'll close that off perfectly over there. So we haven't perfectly completed this code, but essentially we have something called the LFPK, which gets put into the steering, which I'll explain later. But eventually it's going to go into this start moving, which is steering. The steering part is, the corrections, which we'll add. And then the 15 is the speed at which it travels. So this is 15% speed. I'm going to change this to 25 at the start, just because for the example that I have, I use 25. Now let's get into the steering part. This is the most important line in this whole program. This is why I'm explaining it last. So we're going to go 70 minus, and I actually won't put spaces as well because it gets quite chaotic. Get underscore reflected. Make sure everything is spelled correctly. I think I have reflected light, and then put a bracket sign here, and there's a bracket sign to close it off there. So this is one whole big bracket over here. So this is the starting point. These brackets are just on the reflected light, and that's the closing bracket. And then the last thing we're going to do is multiply this whole thing by something called the LFPK. So let me now explain what this does. Make sure this LFPK is the same as that one. As you can see when I highlight that, that gets partially highlighted. So when you're traveling on a line, as explained in the explanation, the main thing you're following is the target value or the target reflection. And for this my situation, I'm going to be using a target reflection value of 70. What you do is you put your robot in between the lines as explained, and whatever number comes up in this top left section over here, that's going to be your target value. Normally in Spike Prime robots, a value of 50 to 70 to 80, that works pretty well. It depends on your lighting situations though and the ambient conditions in your room. So that's basically the set value that we're going to try to hit. Now after that, we have something called the reflected light. This whole line, all it does is get the reflected light that this thing is currently reading. So if it's perfectly on in between the black and the white line, that's going to be 70, and this is 70 minus 70 is going to be 0. So our steering is going to be 0 because it's perfectly on the black and the white line. So we have nothing to correct. Whereas if it's more toward the black line, this number isn't going to be 70, right? It's going to be something lower. So it's something like 50. So 70 minus 50 is 20. So it's going to steer 20 back into that 70 region. And vice versa, if it's on the white line, it's going to go higher, like 90. Again, 90 minus 70. Well, in this case, it'll be 70 minus 90, which is minus 20. Because it's on the white line, it'll go the other way. So if that doesn't really make a lot of sense to you, make sure you've watched the explanation that I wrote a little bit carefully at the start of this video, because this is where I really explain the crux of this. But that's essentially this whole correction thing. All you need to know is that it'll take a number, and according to that number of the light value, it'll steer back in between the black and the white line. So I haven't explained the LFPK yet. What this LFPK is, it controls the rate of correction. So a higher number of LFPK, it'll be a bit of a zigzaggy motion, and a lower one, it'll be more curved and like a slower rate of correction. So depending on your situation, a higher number or lower number may be required, and I'm going to explain two different situations now. So often the two different types of situations where you want a line follow is on a perfectly straight line. So it just goes from one point to the other point, but you want a line follow that to make sure you're traveling correctly. And then you may get situations with a curved line. So I'm going to explain a straight line situation first. With a straight line situation, you can normally go at a higher speed and a lower LFPK. So in my situation, I've got a straight line. I'm going to be using 25 speed and 0.4 over here. And that for me works pretty well. What I recommend when you're traveling when you're using any line follower, set this LFPK to 1 first, right? After that, set your speed. So normally a lower speed is required for a line follower, but you can travel a little bit higher if you have more agile robots. So, less bulky, I guess you can say. So I'm going to be using 25, but set yours to however you like, something under 50, I guess you could say. 50 would probably be the maximum if you want to, really use accurate programming. So I'm going to set mine to 25. And then after that, test how that works. And you'll see that the corrections may be still too sharp. Then lower this LFPK. I'm going to set mine to 0.4. So on a straight line, I got mine to 0.4 and 25. So the last thing we need to do is make sure that our motors are perfectly stopped. So we're going to put motors dot stop. And that's our last line. So on a perfectly straight line, we're going to now test this. Let's see what this looks like. So as you can see, that followed the straight line pretty well. That actually wasn't a perfectly straight line because I made it handmade out of tape. It was probably a little bit dodgy, I guess you can say, but it still followed it pretty well. So on a straight line, this, a higher speed and a lower LFPK is usually the region that you can go. But you probably saw the curve line, which we're going to test next. Now on a curve line, a lower speed, like 15, and a higher LFPK, like 1.5, is more in the region of what you need. And the reason for this is simply because a curved line, there's more value or more region for error. So the margin for error is a lot higher. So to correct for this, we're going to go slower and we're going to make our corrections a little bit faster to, you know, pick up on those errors. Now, I didn't just magically get these numbers out of nowhere. Once again, I've tested my code a few different times, and we're going to actually see what my tested code looks like now. So as you can see, it did pretty well on that curved line. I tried that a few different times, and again, what I recommend, just set this LFPK to 1 and then choose a low speed for a curve, right? And you'll see maybe it still veers off track, then increase this LFPK to maybe 1.2 or maybe 1.3. At some point, you'll see maybe improvements. If it's not improving, decrease it. So I saw improvements going upwards. Keep increasing, all right, slowly. 1.5, try it again. 1.6, try it again. And at 1.7, I kind of saw a decrease in improvement. So that's how I knew that somewhere between, you know, 1 and 1.5 was a pretty good number for me, and anything above 1.7 wasn't going to help. That's why I just chose 1.5, and that's how I knew. So always set your speed first, test it out, and then iterate your LFPK to make sure it's the correct value that you need it. So as you can see, we've essentially created a line follower that can hit a straight line or a curved line. Now, it's not as easy as just pressing a button. As you know, there's a lot of programming involved. But if you're watching this video, you know, you're probably interested, and you've gotten this far, you're probably interested in, you know, knowing the code, and you probably have the determination it takes to get this really perfect. So with that concludes this video. Thank you for watching the whole way. Once again, the line follower is just one aspect. You can also do a gyro straight, you can also do gyro turns and line squaring. So I have more videos in this video series, whether it's in Python or in word blocks. So, you know, definitely browse around and try to keep improving your skills with programming. So with that, I'll see you guys in the next one.